if the light is on 10 minutes before the class, it may be off 10 minutes before the class ends, right? Not a good sign. All right. We can only hope that it's going to work. All right, so we basically, the topics I'm going to be covering in the next few lectures are sort of a review for those who have taken the previous course with me or the similar courses. But I will try to sort of put different spin-off in the presentation so nobody gets bored, okay? So certainly I'm assuming that the class knows what the prior, what the posterior, what the predictive distribution is, etc. And if you don't, you will see this through the examples, and you can come and visit me. I can give you more references if you want to. So there is nothing really complicated that you have to worry. All right. So what I'm going to do is I'm going to introduce Bayesian models for discrete data. And actually, if I remember on my lectures, even in the fall, I don't believe I ever discussed discrete data in any extensive manner. We went directly to regression. So this topic sort of may be new to practically everybody in the class. Do me a favor, by the way, if any of the links is not working, I don't want to have to put the efforts of having links that somehow don't function. So if you see something that doesn't work, just let me know, okay? And that includes the software as well. All right, so what we're going to do is we're going to discuss, we're going to try to bring some ideas of classification models. And I'm interested really on generative classification models. And so let me introduce them with this generic equation from the product rule of probability. So you have some data X, and you're asking what's the probability that this data will come from class C, and theta are some parameters of the model. So for now, you can say you don't bother with theta. So what we do is we write this probability by inversion, effectively using Bayes' rule, if you like, as the probability of X given the fact that the data X come from class C times the prior model that we have for class C. Okay? So these models are called generative because, in essence, to model this, we're required to know how the data of each class look like. Right? We need to have a generative model that allows us to produce X's from each class C. Okay? There are other ways we can do classification that avoid using completely this formula, but what you will hear today and tomorrow in the context of these lectures, we will try basically to model this class conditional density of P of X given the class. Now, these parameters theta that you see, somehow we're going to have to fine-tune them. So if the model has some parameters, we will need to discuss on how eventually we need to compute those. All right. So I'm going to introduce this with an example that it's in Murphy's book that has to do really with, it's a sort of a primitive example that tries to demonstrate that the way the brain works is sort of Bayesian. So it may look a weird example, but it's actually sort of very fundamental to Bayesian thinking. Okay? So let's hope that we understand what is going on. So this example comes actually from the work of Tenenbaum from MIT, back from his early days in his PhD thesis. He almost agreed to come to visit to give a seminar at CICS this semester, so hopefully we will have him to visit in next fall, because he does lots of very interesting things. So let's define the following thing. Suppose that we have a concept C or a hypothesis C, and we have an indicator function that says if some data point is in accordance to this concept C or not. Okay? So if f of x is equal to 1, x comes from this concept C. If f of x is equal to 0, it does not. So you can think of f of x being an indicator function that tells you if x belongs to this concept C. And we will see examples of what this concept C is. So usually in a Bayesian setting, and when you do classification, somebody gives you training data. The training data don't have to be positive examples, like this point belongs to this class, this point belongs to that, you know, can be positive and negative, but in the context of psychology and the way the brain works, we will only operate with positive examples. The idea here is that human beings learn from positive statements, not from negative statements, okay? Believe it or not. Okay, so so that's basically a little bit of a highlight here that we will only use positive examples. And the example this concept we will use is related with what we call a number game. So let me discuss what the problem is. So we are going to work with numbers from 1 to 100. Okay, so every number is supposed to come from 1 to 100. And the concept C that I introduced there, it's a concept that says, how do I generate the numbers from 1 to 100? So for example, you can say, the concept C is even numbers, or odd numbers, or powers of 2, or numbers that finish in 7, or powers of 10, or something like that. So that's the concept C. And the setting is the following. I give you some numbers, and I want you to find what is the concept C that goes with those numbers. Okay? And the way that Tenenbaum did this analysis, he basically used empirical measures, asking people, you know, if you have this number, can you give me some similar numbers? So he did some probabilistic analysis using empirical data, and then he demonstrated that somehow a Bayesian setting produces more or less the same results. So we would like to sort of go and revisit this type of concepts, and in the process basically discover what's a prior, what's a likelihood, what's a predictive distribution, and all the classical Bayesian concepts. But remember, you know, in a Bayesian setting, basically, what of interest to us is to do predictions, basically. You know, so you know the idea here is if you know, if I give you this data, and you may go and figure out that they come from this concept C, but eventually at the end of the day, I would like you to tell me, if I give you a new point, if it actually belongs to that concept C as well. That's the prediction. Okay? All right, so what we have is numbers from 1 to 100. Okay? And I'm going to give you one data point, and I'm going to tell you I have a data point 16. Okay, so this is my data set. The data set consists only of the number 16, nothing else. And you remember, I only work with positive data, all right, that follow the concept. So the question here is, I am asking you, without any statistics, what other numbers basically are positive, consistent with this concept C, from where the number 16 comes. Now you may say, you know what, 16, you don't give me enough of information, but still your brain will start giving me numbers that somehow you may think they are related to 16. So you may say, oh, you know what, 17, because it's close to 16. Or you may say 1, because it's part of 16, or 6. Or you may say 32, because it's 2 times 16. All right? But it's not enough information. So basically, whatever statistics you'll be able to do this way will be very diffuse, because you don't have enough data to do the analysis. But somehow your brain, you know, just thinks and says, yeah, 32 sounds reasonable, 2 times 16. So what we want, so the problem, you remember, is we want to be able to do predictions, and probabilistically, basically what we want is to produce this predictive distribution for any new data point x. So if I ask you, is 17 consistent with this concept C, you're going to have to produce for me the probability of this new x given my data set D, all right? With the only constraint again that all my data points are from 1 to 100. So this is what we call the posterior predictive distribution. So given the data D, we want to find if this curly x belongs to the concept C, okay? And all this is expressed with this distribution, the posterior predictive distribution. All right, so let's start showing some real numbers. So we are going to do different cases, all right? So in the first example, the data set is only the point 16, okay? On the second example, the data set is only the point 60. Here I have 4 numbers, and here I have another 4 numbers. So what this empirical predictive distribution is effectively asking people to give you their thinking if different numbers belong to the concept from where 16 came from. I mean, I derive 16 with some rule, but I'm not telling you. So what the idea here is, you ask each of you and you say, is 4 consistent with the concept related to 16? You say 4, 16, yeah, right? And so what you do is you create a histogram, and that's an empirical predictive distribution. And what you see here are basically real data averaged over a number of people. So if you tell them this is the only observation, this is the empirical predictive distribution. If you observe 60, this is the empirical distribution. And you notice, it actually, if you pay attention to the numbers, it's interesting. Here everything around 16 seems to be consistent when it comes to the evaluation of the people. Think, all the numbers around 16 are consistent, but then there are some numbers, 64, all right, and 96, because they're multiples of 16 that they're consistent as well. In this case, where the number is 60, people say, you know what, lots of numbers around 60 looking reasonable, all right? What's the concept between 16, 8, 2, and 64? What do you think people will say? It's powers of 2, and this is what you get here, all right? And in this case, again, I see that everybody basically concluded that there are numbers around 20. 16, 23, 19, 20, so basically the histogram looks like that. There is nothing Bayesian, basically, by the way, on this. This is just an empirical predictive distribution, but somehow it would be of interesting to know why, from where is this coming logically, and is this consistent with the Bayesian formalism that we're interested to learn in this class and in machine learning. All right. So, don't need to tell you all of these things. So let me introduce first the likelihood model, and hopefully you know the concept, right? So what is the likelihood model? If I give you the concept C from where the data come, I want you to tell me what's the probability of that data. Okay? So if I tell you that I am selecting numbers that they are odd from 1 to 100, okay? And all these odd numbers from 1 to 100 are equally probable, I would like you to tell me what's the probability of my data. That's what the likelihood model is. So given the hypothesis, H, I would like to know what's the probability of the data that I have observed or I gave you. And this equation is extremely important, okay? It sounds very trivial. So what we're going to do is we're going to assume that so if I, how many, let's say, odd numbers we have from 1 to 100? How many? 50. Okay, so we're going to assume that each of them is equally probable. So the probability of selecting each of them is 1 over 50. So you notice here it says 1 over the size of this concept H. So if it is 50, it's 1 over 50. So if I select, let's say, n data points, the likelihood would be 1 over 50 to the power n. Okay? And interestingly enough, when you look at the likelihood model, can you tell me what type of hypothesis it supports mostly? So if you have different observations and you try to see which hypothesis, which model, which assumption H produce, which concept C produce this data, which model of what size do you think is the most probable?
You don't have the microphone?
It doesn't matter because there is a microphone here that it told me it works and it captures you asking me too. Okay? But since you are asking me, I look better with the microphone, so I'm going to put it as well. So, so the question was, according to this formula that you see there, which concept is maximizes the likelihood of the data? Which one? Well, if I give you n data points, right, I have different concepts, multiples of 5, powers of 10, even, odd. Which of these different concepts is the one? I don't want you an answer, I want you in an abstract answer, looking at this formula, for this is the number of elements in each concept. Which concept maximizes the likelihood of the data? The minimal sizes, right? And that makes sense because if you have too many elements, right, in that hypothesis, the chance that you will select a number from this will be smaller if the more you have, all right? So really, this already incorporates, if you like, a complexity control in the problem, and it says that models that are simpler are actually preferable. And that's a Bayesian way of doing things, okay? So what he did is he used this very simple likelihood model. Again, this is how many elements I have, how many numbers in that hypothesis from 1 to 100, and we assume the data to be IID, so the probability of the data given the hypothesis H is 1 over H to the power n. So H is the number of elements, is the size of the hypothesis. So let's, for example, take the case of data that is only the number 16. So, so if we take the hypothesis that there are powers of 2, okay? All right? So the probability is 1 over 6. You know why? Because there are only 6 powers of 2 less than 100. Now, if you take that this even, there are 50 numbers, so the probability is 1 over 50. And actually, okay, in this case, we only have 1 data point. So obviously, the likelihood of this, way bigger than the likelihood of that, which means from the likelihood alone, the probability that this data point was produced from a model that it's derives numbers from powers of 2 is much higher than from a model that takes basically even numbers. You see that? Yeah? All right. And of course, you know, if you have, let's say, more data points, right? You can see if you, let's say you have 4 data points and you take 1 over 6 to the power 4, then this becomes 10 to the minus 4 versus 1 over 50 to the power 4 becomes 10 to the minus 7. So basically the likelihood ratios is now way in favor of having a concept that is produces numbers that are a power of 2. Okay, so that way, for example, when you look at the data set that looks like this, just on the likelihood alone, all right, everything points that the hypothesis is powers of 2. Okay, what we need now is we are gonna, so we bring things closer to the Bayesian setting. We're gonna need some prior on the hypothesis, right? So, you know, if you're gonna have different hypotheses, you can just give me a very weird hypothesis. You can say something will start at 1 and finish at 7. And I'm going to tell you, forget it, probability 0.01. So you would like to introduce that knowledge in your problem, okay? And more importantly, for those who have done this before, you know, if you don't have a prior on the hypothesis and your sample size is small, like for example, when we had only the number 16, it's very difficult to do any inference. All right? It's very difficult to actually do any inference. So in that case, having a prior model is essential. So what you see on the top is Bayes' rule, right? Hopefully it's not the first time that you see it. We remember we had collected the data D. So this is the likelihood P of D given the concept H. This is the prior, right? And what we have here is the probability of the concept H given by data D, okay? On the top what we have is a normalization factor. And I plugged in here an indicator function. Can you appreciate why I have an indicator function there? Why I need it explicitly to be precise? I mean, this indicator function says that all the data points have to be positive data points. They have to belong to the concept H. Because if they don't, then the probability is 0. Right? There's no point of writing this equation if the point is outside that concept. The probability would be 0. Okay? So the idea here is, we just want to emphasize this. And this is the likelihood, right? 1 over the size of H to the power n. All right, so let me start introducing some other Bayesian concepts that you have seen before. If you have lots of data, all right, this posterior effectively becomes very sharp. Okay, so a typical thing you can do is approximate this as a delta function at the mode of the distribution, and that's the map estimate. Okay, so basically the map estimate is defined by maximizing the posterior, and in the context of a lot of data, you can approximate the posterior with the delta function. Okay. There are better ways of doing this, and we will see this in this class, but this is what the definition of the map estimate is, basically approximating with a point estimate, if you like, the whole distribution. So if you want to find the map estimate, really what you need to do is, if you look at this equation here, this is a normalization factor. H has been integrated out, so really what you need to do is, you need to maximize the numerator. And if you do this on the log scale, usually we will operate with logs. Effectively, the map estimate is the H that maximizes the log of the likelihood and the log of the prior. All right? Since we talk about the map estimate, if you don't include the prior, effectively you can also define the maximum likelihood estimate of H, which is the H that maximizes the log likelihood that you see here. Okay? So we have a map estimate and we have an MLE estimate. And hopefully today I'm going to show you how both of these estimates actually can be very misleading when you try to do calculations. All right, so let's go back to the example. We haven't finished with this example, we haven't done anything yet, to see why the brain operates sort of in a Bayesian setting. So what you see on the left column are all the different hypotheses you can put for generating numbers from 1 to 10. Some are sort of weird, even and odd and squares, so basically some powers of something, multiples of 3, etc., and some other weird ones. So some that are very weird, you assign 0 prior probability. If you say even and odd, you put higher probability, and the rest, you don't know anything, so you just put them equal. So what I do now is, so this is my prior on the left. I collect data d equal to 16, that's the number I give you, all right? So the likelihood model, all right, will be the probability of generating 16, but 16 can only be generated from a few models, all right? So for example, the model that says odd cannot generate 16. So the likelihood there is 0. So what you see here are basically the probabilities of generating 16, and that is non-zero only for a few of the models. So for example, I'm looking here, it says powers of 2 minus 32. Obviously, powers of 2 can generate 16, so there's a high probability there. And here it's powers of 4. Obviously, this is a very high probability. All right, so this is the likelihood. And the only thing that I use in generating the size of the numbers here that we see is the size of every hypothesis. You remember when I say this is even and odd, right? There are 50 numbers, so the probability is 1 over 50. So if I only have one number, the likelihood is 1 over 50. This is what you see on this column. So the posterior, if we don't bother about the normalization factor, is nothing else multiplying each row here in this first column with each row here. The zeros, of course, will propagate. If you have zeros in the prior, it will give you zeros here, or if you have zeros in the likelihood, they will give you zeros here. So basically what you see here is the posterior. So effectively, it tells you that the number 16 can be generated from the concept that the numbers were even, or the concept that this is the squares of something, from a few concepts. So given 16, this is what you come from. Okay? Now, if you repeat the same thing and you have more evidence, So you have 4 numbers. You notice, literally you repeat exactly the same analysis, and suddenly you are left basically that if you have those 4 numbers, the only way that those 4 numbers will come is from being powers of 2, nothing else. 4 numbers basically tell you what the concept is that generated the numbers, okay? Now, when the analysis was done, right, and I showed you the empirical distributions, people did this in their minds, and they said, no, there's no way for this, there's no way for that. But what you see here is effectively a Bayesian setting by setting a prior for the hypothesis, having a likelihood model with the size of its hypothesis, and then a posterior model. It basically brings you close to what exactly you will think using common sense. All right. So if you remember, of interest is to do predictions, right? We don't just, we want to produce the posterior of the hypothesis, but we need to do predictions. And the predictive distribution is, given the data, I want to find the probability that a new point belongs to that constant C. And you can think this even in the context of classification, right? Given the data, I want to know if this point belongs to this class, okay? I am not going to do any derivation because it's really the sum and product rules of probability. But for those who forgot, the predictive distribution literally is an integral, or here a summation over the hypothesis H, or the parameters, if you like, of the likelihood. So if I knew the hypothesis, what's the probability that basically this point X would be a positive example, all right? It's written like that here, so Y means that X belongs to this concept C, and this is the posterior distribution. Remember, predictive distribution, integral of the likelihood times the posterior, integrated over the space of all the parameters. In this case, there are no parameters, the hypothesis H, averaged over the hypothesis H. This equation to do predictions is the Bayes model averaging, basically, that says, look, different models can produce these numbers that you have observed. So what you need to do to be able to do predictions is take the likelihood from each of these different models and average it with a probability that the posterior probability that each of these concepts is consistent with the observations that we have. Okay? So nothing fancy, all right? And we will see this formula in many ways. Again, integral or summation, the likelihood times the posterior, okay? So let's see what this calculation will do, right? So what you see here is, again, each row corresponds to a different concept. So I see here, it says even, multiples of 8, powers of 2, powers of 4, etc. And the numbers there you see are all the numbers from 1 to 100. And when you see under a number a dot, means that each of these concepts is consistent, all right? So each of these numbers is consistent with this concepts. So for example, there is no dot here, which means that 100 cannot be produced by a powers of 2 minus 32, okay? So effectively, each of the numbers, like 64, can be produced from this concept, that concept, that concept, that concept, etc. All right? So 64 can be produced by lots of concepts, okay? And what you see on the right is basically the posterior distribution of each of the concepts. And I already explained to you how we compute the posterior distribution using Bayes rule. So you notice here, given a data set D equal to 16, okay, this is what we used for this example. These are the posterior distributions of the concept that the model, the concept H is powers of 4. And notice, this has the highest probability, right? Powers of 4 gives you 16, okay? Then powers of 2, very high probability, but then all of the other things, you know, the probability is being reduced. So effectively, this summation, you know what it is like a weighted averaging of these dots, of the likelihoods of the data under each hypothesis, weighted with the values of the posterior distribution. Again, I mean, this is sort of the classical Bayesian setting where you say, to do predictions, you're not going to use one model, you're going to average over all models that explain the observations. And what you have here is, you have, again, the likelihood of the data being generated, of x, curly x generated from concept C, times the posterior of concept C, okay? And this is the posterior, here is the likelihood effectively, and when you do all of these things, you get the predicted distribution that looks like this. So somehow, if you only observe 16, nothing else, what you see here, it tells you the predicted distribution of observing 4, very high, you notice this, 16 obviously very high, 64 very high, and some numbers are 0. Very nice calculation that somehow out of nowhere you can assign probability of your next observation, let's say, being 72. It's not 0, it's significant. And all of this comes basically by this model averaging that you see there. All right, so we can introduce more Bayesian formalism here, or some terminology if you like. I indicated, right, on the predictive distribution is basically this summation of the likelihoods times the posterior. So we take the sum over all possible concepts that explain the data, where the weights are the posterior. So what we can do is, since we introduced the map estimate for H, we can substitute the posterior distribution there with a delta function. So if you have a lot of data, the posterior distribution is around basically one concept. So that one concept, we will call it H hat. So let's say this is the concept of powers of 2. So somehow, being able to do predictions, the only thing that requires you is to use the likelihood model, but for H, use the map estimate of H. So this is what is called in Bayesian setting, is called the plug-in approximation. Right? You use your likelihood, but for parameters or hypotheses, you use basically the hypothesis that maximizes the posterior. So you don't average, you use the hypothesis that best explains basically the observations that you have. Okay? So this integral or summation here becomes a point estimate. I mean, this is how do you do, you know, what's the likelihood model? The likelihood model is given H, tell me what's the probability of X, all right? So here, for a likelihood model, we use the one that has the maximum posterior probability. Okay? All right, so just so I can finish this basic sort of example with this Bayesian way of playing this numbers game. So what Tenenbaum basically did in his thesis, literally, he concluded that the prior model, with the rules that I show you, it's not the way actually the human beings behave, and somehow you need a mixture of priors, one that comes from numerical rules, and another one that comes from interval rules. So you can say, you know what, I would like to assign more probability to be around 20, but don't tell me a rule that generates those numbers. So he used a mixture of a prior based on rules, like the ones we show, powers of 2, even, etc., and a rule based on intervals, okay? And from analysis basically he concluded that the results are not sensitive to this mixing coefficient if it is greater than 0.5. So what he did is he used this prior model to compute the predicted posterior distribution with the way that we discuss, using this formula here. Right? So instead of using the prior model, the numbers that I show you, there was a previous diagram somewhere, I show you all these numbers here based on numerical arguments. What he used is a more complex prior, and using this more complex prior, he came up with the predictive distribution looking like this. So what you see here is the predictive distribution computed with Bayesian analysis, rather trivial, for different data sets. This is when you collect only the point 16. This is when you have a data point 60. This is you know, I cannot see the numbers clearly, the 4 numbers that I had before, right? And what you see on the left is the empirical predictive distribution. It's basically the distribution that comes up by asking many people on what they think the concept is and how these numbers were generated, and then averaging over many people. So you can see that the Bayesian formalism gives you very close answers to the empirical predictive distribution. I mean, you don't really see sort of out of nowhere a Bayesian analysis that somehow seems to be consistent with non-mathematical arguments, right? The way that sort of the brain looks and makes observations and then makes decisions. So this empirical predictive distribution, that's like a histogram averaged over various people. Each of these rows is for a different data set, okay? So in the first case, the data point is 16, so you can see the empirical distribution is around 16, basically, more or less, but some other numbers that they are multiples of 16 are consistent. The same thing if you have an observation 60, numbers around 60 is what you get. But if you have more numbers that are powers of 2, you can see precisely how the predicted distribution looks like. And in the last case, the numbers are basically the ones that they are around 20. All right, so what we have seen up to now is, if I can put this up, right? So we discuss about some concept aids, some hypothesis that we want to do inference about, all right? We will see actually today with simpler examples. This can be parameters of the model, but right now, in this example, this was a hypothesis. So this was a likelihood model, okay? This was a prior model. This is the predictive distribution, and we discuss also this point estimates, the map estimate, and the MLE estimate. All right. So what I'm going to do is I'm going to go very elementary now, all right? And I'm going to repeat these things with examples that sort of are for statisticians, 101, okay? Not anything complex as the way the brain behaves, but, you know, so in some sense, if you understand the examples that we did before, they are more fundamental to Bayesian analysis than the things you will see here, because what you will see here is a machinery of doing algebra, not necessarily something that comes with easy going explanation. All right, so I'm gonna try to work with the coin toss problem, okay? And I'm gonna try to tell you things that you don't really know, all right? Even if you heard this many times, so hopefully I will not bore you completely. So we toss a coin, and I'm gonna call the probability of being heads theta. So I don't have a hypothesis now the way I had, right? I have some unknown parameter on my model. I don't know what's the probability of hitting heads. I don't know if this coin is a fair coin or not. So I'm going to model the outcome of its experiment with a Bernoulli distribution. So the Bernoulli distribution for binary variables, it tells you x will be equal to 1 heads with probability theta, and it will be 0 with probability 1 minus theta, okay? So the likelihood, so if you throw the coin a few times and you collect a few heads, a few tails, and I call this the number of heads n1 and the number of tails here n0, the likelihood model is theta to the power n1 times 1 minus theta to n0. We agree? So if you hit heads and n1 times, like all these experiments are independent of each other, so it will be theta times theta to the power, so theta to the power n1, and then n0 tails, so 1 minus theta to n0. Okay? And I indicate the definition of n1 nicely using indicator functions. All right, this is how you need to do it. So you go through all the data set and you measure how many times you had heads, that's n1, how many times you had tails, that's n0. So notice when you do this coin toss problem and you write down the likelihood, you can actually completely disregard this observation xi's. Really what you need to care in computing, let's say, an estimate of the parameter theta is n1 and n0, right? These summations that you see here, because in the likelihood model, the individual x's have disappeared, okay? By the way, I will never post my presentation again on the web until I give the lecture, because I see some just like that on their computer. I'm assuming you look on my lectures, you may be looking on something else, right? So these numbers n1 and n0 that you see here are the only things that you need to know to compute theta, and they call the sufficient statistics of the data. All right? So they're basically some compound functions of the data, all right? And you can throw the individual data away, and the only thing you need is n0 and n1 and n0, and this is what we call the sufficient statistics. And there are two numbers, basically. So actually, you know, because n1 and n0 is the total number of trials n, really it's one number n1, because this is n minus n1. Now, if instead of this Bernoulli model, you know, you want to use you know, the binomial model, effectively you get the same likelihood except this normalization factor on the front. So, you know, the two things basically will give you the same ideas, the same likelihood. Okay. So let me repeat. We throw the coin n times. We get some observation, n1 times heads, n0 tails. And this is the likelihood model, okay? And we would like to do inference on theta, all right? So the first thing you may ask is, can I do a maximum likelihood estimation of the parameter theta? So can you do it for me? Because, you know, I am not gonna be doing algebra as trivial as that, because we will never advance in the course. So if you try to maximize this and take derivatives equal to theta, and you set them equal to 0, what do you get? Usually what you get is the common sense answer. So what would be the MLE estimate for theta? I don't hear a thing. N1 over n, right? The empirical count, basically. This is what you will get out of this thing. Okay, all right. So what we will do is now we will try to use a prior model, because if you have very few data, the concept of using the likelihood alone to do the estimation is not appropriate. So we're going to introduce a concept, if you have not heard this before, that is called the conjugate prior. So remind me, what's a conjugate prior for those who have seen this before? So it is we call this to be conjugate to the likelihood that I showed you on the previous slide, if it is such form that the posterior has exactly the same form as the prior, just with updated parameters. And indeed, you can see this. You remember if you write the posterior, the likelihood times the prior, the likelihood was theta to n1 and 1 minus theta to n0. So if you use this prior model, okay, and this prior, by the way, here, it's, you know, we will see on the bottom, it's a beta distribution. So effectively, what you do is the parameters gamma 1 and gamma 2 that you had in the prior are now updated to n1 plus gamma 1 and n0 plus gamma 0. Okay? So this is, it doesn't mean it is the best prior, right? But it makes life easy, because calculations are trivial. The only thing you need to do is update the parameters gamma 1, gamma 2, which are sort of what we call the prior counts, update them with the empirical counts n1 and n0, and then immediately you can see the distributions of the same form as the prior. So that distribution effectively, and the conjugate prior that we will use is a beta prior that looks like this. Okay? So a beta prior, when you see theta to some power, 1 minus theta to another power, right? This is the nice conjugate prior. I don't really expect you to remember all the distributions, but if at the end of the day, you start doing some things by hand and you play with these things, you will remember it, okay? And if you're like me, every time you need something, you hit Wikipedia and there is everything you need to know, so no excuses, I don't know what that is, etc. If you want to know the mean, the variance, or whatever else, hit Wikipedia and you will come up with all the answers. All right, so the posterior is also a beta distribution with parameters now n1 plus alpha and 0 plus beta. And you know, one of the sort of justifications of using this conjugate prior is effectively you can interpret this alpha and beta as prior measurements, prior number of heads and prior number of tails, if you like, because they somehow they come when you compute the posterior, alpha and n1 are added together and n0 plus b are added together, okay? So this is actually not just for this particular problem, but for the whole family of these conjugate priors, you can make sort of a similar conclusion. All right, so a simple example for this coin toss problem. The prior here is very diffuse, as you see. So it's all over the place. So basically you say a fair coin has the highest probability, but unfair coins are also okay. You collect some data. Does it say what data we collect? Well, here it is, sorry. So 3 heads, 17 tails, okay? So the likelihood is this dotted black curve. And because the prior is very diffuse and you have a lot of data, the posterior, this blue curve, it's only slightly move you know, towards the prior, but not to a significant degree. Now, if on the other hand you have 11 heads and 13 tails, you know, it's like you're almost 50-50, right? Things are a little bit confusing here. And you can see in this case, using this prior, okay? So here, you know, that you basically, you put more probability that the coin is not fair, okay? And you can see this, the distance between the likelihood and the posterior is significant. All right, so let me bring some elementary concepts that they're essential to machine learning, and almost everything we will do with many types of calculations, way more complex than what you see now. So this is the posterior. For the coin problem, we said is a beta distribution. And here I cut and pasted formulas from, you know, from tables that gives you basically for the beta distribution what the formula distribution, the expectation, the variance, and the mode. So you notice here the mode for the distribution beta alpha beta is alpha minus 1, alpha plus beta minus 2. So the mode, the map estimate for my posterior, it's this form that we see up there. Okay? It says here alpha minus 1, so it will be n1 plus alpha minus 1, alpha plus beta minus 2, so this plus that minus 2. So the map estimate looks like that. All right. So let's see some interesting things. If you remember, so the beta distribution, right? We use a prior that was a beta distribution. So this beta distribution becomes a uniform distribution if alpha and beta is equal to 1. You see that? So it becomes completely an uninformed prior if you put alpha and beta equal to 1. So if I go to this map estimate and I put alpha and beta equal to 1, alpha and 1 will cancel, alpha and beta 2 will cancel, and then the map estimate becomes the same as the MLE estimate. Okay? So that's, you know, one interesting aspect. The other aspect is if you try to calculate the expectation of this posterior, so the expectation here you see is alpha divided by alpha plus beta. That's a good formula to know. So it's n1 plus alpha, and I call here alpha as, I define m1 to be alpha divided by alpha 0. All right? You can actually, this would be the prior mean. All right? This would be the prior mean. So you can see that the posterior mean, you can read more and see the calculation is just one line, you can see that the posterior mean is a convex average of the prior mean and the MLE estimate. And this is very important because this type of averaging is going to be coming in lots of the calculations. And in some of those calculations, rather than using lambda to be precisely what we derived in this model, we will manipulate lambda to make this posterior estimate more stable for certain calculations. Okay, but right now you can see, not surprising, that the posterior mean is the average of the MLE estimate. The algebra, again, there's nothing there. It's an average of the MLE estimate and the prior mean. And lambda in this case is this alpha 0 divided by alpha 0 plus n. And what is alpha 0 is, alpha divided by m1, where m1 is the mean of the I have defined alpha 0 here, alpha plus beta from the prior. All right. You can actually, if you are interested, to do some little homework calculation. So here what we did is we showed that the mean of the posterior is this convex average of the mean of the prior and the MLE estimate. You can actually show the same thing for the map estimate of the posterior. So you can also show that the map estimate is a convex average, basically, of the prior mode and the MLE. And you get sort of a similar type of expression. All right, so if you want to get the variance, all right, so the variance, I'm just copying the formulas that you see here. The variance of the posterior looks like this. And if you assume that you have a lot of data, you can get rid of the prior coefficients alpha and beta. They are insignificant versus the numbers of heads and tails. So you can write the variance as n1 times n0 divided by n cubed. And n1 over n is the MLE estimate. So the variance is really theta times 1 minus theta, where theta hat is this MLE estimate. So what we have is, you have error bars, all right? You have error bars in the estimation of theta. So you can say in this case, your estimate is theta hat, but your confidence on it is plus minus sigma, and the sigma comes from the variance computed for the posterior. And actually, interesting enough, when if you read carefully the slides, and if you look at this variance here, right? So this is your uncertainty about the prediction of sigma. When is this variance equal to 0? When it is 0. When theta equal to 1 or 0, you know what that means? That you are way more confident if this is an unfair coin in the two extremes than if it is a fair coin. If it's a fair coin, the uncertainty is the maximum. Okay? And you can think about it because that sort of has some philosophical implications. All right. Remember that the calculation we really care when we do Bayesian statistics is to do the prediction, okay? So, and the predicted distribution now is, the meaning is the following, right? So we collected some data, some heads and tails, and that's my data set D. And now you're asking, if I throw this coin once more, what's the probability that I will get heads? And I remind you that predictive distribution is an integral. Before we had summation over A, so it's an integral now over the parameters theta of the likelihood. What's the probability of getting heads? Is theta. And what is this? This is the posterior, all right? And if you look carefully on this, the predictive distribution, you know what it is? It is really the expected value of the posterior. This is not surprising because this is a binary problem, right? I mean, you either have heads or tails. So if you use the definition of this expectation, you will immediately come up that this is equal to that. But the idea here is the predicted distribution, all right, is the mean of the posterior. This is the correct calculation. This is the mean of the posterior. So if you compute the mean, right, from the formulas I had before, the mean is n1 plus alpha divided by n plus alpha plus beta. Alpha and beta were the coefficients in the prior model. So look now what happens. If you go and use an uninformed prior, so if in your beta distribution the coefficients, so you remember the beta distribution is theta to alpha minus 1, 1 minus theta to beta minus 1. So if you take alpha and beta equal to 1, you basically get a flat uninformed prior unnormalized equal to 1, okay? So if you put this equal to 1 and this equal to 1 plus 1, you get that the predicted distribution is n1 plus 1, n plus 2. So actually, even though the prior is uninformed, the predicted distribution is way much informed. Have you noticed the result here is not n1 over n? Even though we have not really assumed anything for prior, but somehow by averaging over all possible models, there is some smoothing effect, some regularization if you like, in the predicted distribution that is called n1 smoothing. And it only happens when you compute the mode of the posterior. It will not happen if you use the MLE estimate or if you use the map estimate, but if you use the mode of the distribution, you have n1 plus 1 and n plus 2. So you say I use an uninformed prior, all right? But is it really uninformed? How uninformed is? Well, how can it be uninformed and still you go and you add 1 and 2 there? So think of the following. If you do an experiment and you never observe heads, this model will tell you that the probability of observing on the next experiment heads is not 0. It's going to be 1 divided by n plus 2. If you don't do this right, and you have very few data, and if I throw this coin 2 times and it comes to be tails, all right, you immediately will say, oh, you know what, I will never get any heads. This says, no, wait a second, you don't have enough data, there is a probability of getting heads, and that is 1 over n plus 2. Okay? That's very important. Now, if you somehow, if you try to do this type of, if you try to use the MLE estimate or the map estimate, and you try to do, to use point estimates to do this prediction here that you see, you are not going to get this n1 smoothing effect, okay? So for example, if you try to use here, all right, if you try to use the map estimate of the posterior, all right, what the result will be? The result, if you put a delta function here centered in the map of this posterior, basically what you will get from this calculation, you will get the mode of the posterior. And the mode of the posterior is given like this, right, from the formulas. And if you put alpha equal to 1 and alpha 0, the alpha plus beta equal to 2, then effectively you don't get any smoothing effect. Okay? So the idea here is if you have very few data, using the mode of the posterior, and in this case, because it's the same as the MLE, is the wrong way. And that's sort of, as you know, that's the black swan paradox, right? So if you have very limited data, so if you only observe 3 tails, don't go and conclude that the next time you will not see any heads, all right? The way this calculation that uses a point estimate based on MLE tells you, but you have to use the mean of the predicted distribution that you see here that does this n1 smoothing effect. This is very fundamental. So this is a toy problem, right? But it is sort of very common. So lots of times when you see calculations, people do this smoothing without sort of even telling you, because this is what you get when you do the algebra. Okay? And you get this only when you use the expectation, not when you use the map estimate, and not when you use the MLE estimate. All right. You can do exercise on this for the rest of your lives, right? And this is not the purpose of this course, but you may ask, how about if, let's say, I'm going to do M future experiments, and I want to know what's the probability from these M experiments X times to get heads, okay? So basically what you need to do is you need to use this multinomial likelihood. There is nothing, so this is the prior, this is your new likelihood, and actually what you get here is you get the normalization of a beta distribution. So this predictive distribution comes to be this nice looking expression in terms of beta functions. I mean, one of the things that I always say to students is, in statistics and Bayesian statistics, everything is trivial, but when you start with something trivial, you can get something very complicated. And this is not really very complicated, but still you can appreciate that things from simple start getting complicated, but really, if you understand the concept on what's going on here, I mean, I just put the new likelihood, right, and the prior. This has no theta here, has no theta, and the rest comes to be the normalization factor of a beta distribution, and the normalization factor of a beta distribution is actually these beta functions, or you can write it in terms of this ratio of the gamma functions that you see on the tables below. All right. So let me show you this example, right? And to emphasize this concept of this plug-in estimate, okay? So what's the plug-in estimate, remind me? Like in Bayesian, when you do predictions, what do I call plug-in estimate? The actual predictive distribution is an integral, it's an average over all the parameters of the likelihood times the posterior. What is the plug-in estimate? So basically, use a point estimate for your posterior, all right? So the idea is you say that with lots of data, the posterior will be a delta function around theta map, and effectively, if you want to do predictions, it's like using your likelihood, but for parameter, you're going to put the map estimate of the parameters. So what you see on this little toy example, we suppose we have collected 3 heads and 17 tails, starting with a prior that looks a beta 2, 2, and then we want to predict what is the posterior distribution that in the next m tosses of the coin I will have x heads. So the posterior plug-in approximation is basically using the likelihood model, which is a multinomial distribution, where instead of theta, I'm going to plug in the map estimate of theta. All right? So what you have on these 2 plots on the right here, on my right, you can see this is the true predictive distribution. If you do the integral, right, this is what you get. And this is what you get with a plug-in estimate. And immediately something you will notice is that the actual predictive distribution has fatter tails than the plug-in estimate. And maybe those who took the class from in the fall or other classes in ACMS, maybe can tell me why fat tails are good. Where do they make a difference? Outliers. Okay? So if suddenly, of course, this is a binary problem, but if you have some data point that comes out of nowhere that should not affect your calculations, this will be less sensitive than this, okay? And again, you can see this with a trivial example that the predictive distribution here is fatter tails, and it's more outspread than a point estimate based on map. All right, so let me start moving forward with a bit similar problems, but a little bit of higher complexity, okay? So this is the Dirichlet multinomial model. So before, we talked about the coin problem, heads or tails, so it was a binary problem. So now we're going to collect data x1 to xn, but we're going to assume that each of these x's can take k different states. So it's not heads or tails, but can be state 1, state 2, or state k. All right. So each of these x's can take any values from 1 to k. Okay. And so what I'm going to do is I am going to affiliate, right? So this is the likelihood model. All right. So look at this equation and define me everything you see in this equation. So what is nk? So I do n experiments. So what's nk looking at that equation? Just read here. What does it say? What is nk? I do every experiment, right? And every point can, if let's say k equal to 3, in each experiment, either I hit, let's say if k is equal to 3 and I have 3 bins, either I hit the first bin or the second or the third. So what is nk? The number of times I hit bin k, all right? And what is theta k? Is the probability that I will hit that bin k. So it's sort of an extension of what we saw before for the binary problem, but instead of having, before we had, remember, theta times to the power n1 and then 1 minus theta. So here we put all together as the product over k with the understanding that the summation of the theta k's is equal to 1. All right, so this is sort of a generalization, if you like, of this binomial beta type of distribution calculations we saw before. All right, so we need to find a conjugate prior to this, right? And so if the likelihood looks like this, we will need to find a distribution to use as a prior that somehow it's a product of thetas, of these probabilities for all the k's, to some power, and that distribution is the Dirichlet distribution that you see here. I don't have time to sort of tell you things that I would like you to know about the Dirichlet distribution because it's going to come up in our calculations in the semester. So can I ask you to just look at least on Wikipedia to see how it looks like and what it means? And it's an essential distribution for many problems, especially in non-parametric statistics, but it looks basically like this. And I give you lots of interesting calculations, all right? So I give you the mean of each of the theta j's. Notice is a distribution of theta, right? So these are the probabilities, and I want to compute them. So the prior is on theta. So there is an expectation for each of the theta j's, a variance, a covariance, the modes. You don't need to derive any of them. They're ready for you to use them. Okay, so so this is the Dirichlet distribution. So what I'm going to do is I'm going to go back to the Bayes rule. The posterior is going to be the likelihood times the prior. So you remember the likelihood was a product of this theta k's to the power nk, and this is the prior. So effectively what you get is you get that the posterior is a Dirichlet distribution. So basically here the Dirichlet distribution is the conjugate prior because the posterior has exactly the same form as the prior. So what we need to do is, and hopefully we have 5 minutes to complete this, I need to tell you how you get the MLE estimate and how you get the map estimate. And so you know how this thing works for this Dirichlet multinomial model. So what we're going to do is we are going to let's find the map estimate, and I work with logs of this distribution. All right, so I'm going to work with logs. So you can see the product is going to become a summation. So from the first term, when you take logs, you're going to have nk log of theta k, and then you're going to get alpha k minus 1 logs of theta k. And what is that? I mean, I'm going to find the map estimate, which means I need to maximize the posterior, but I also notice here I put some sort of penalty term, or a Lagrange multiplier term. Because I want to do the optimization problem to compute the parameters, right, the map estimate, but I want to be sure, since these are probabilities, they sum to 1. Okay? All right. I will not bother to do the algebra. It's everything. It's in the slide. So what you need to do is take derivatives with respect to lambda equal to 0. Take derivatives with respect to theta k equal to 0. And when you do this algebra, basically what you get is that the map estimate for theta k looks like this. Okay? And again, you see that you recovered basically if the Dirichlet prior, it's sort of uninformed. So if all the coefficients alpha k are equal to 1, this cancels. Alpha 0, it was written on the previous slide, is the summation of all the alpha k's. So it will be equal to k. So basically, if the priors are informed, you go back to the MLE estimate, and similarly to the beta distribution, this is not what we would like. It doesn't have this end-one smoothing effect, all right? But somehow, right? Somehow, when you compute the predictive distribution, right? The predictive distribution, so here is, what's the probability that I will hit bin J, all right, given my data set D, and you do the algebra, you get this nice formula. Can you look at the algebra? Am I doing something magic there? What exactly is going on? There's lots of symbols there. Can you tell me? So I see the likelihood there, right? I think I see the posterior. So what's all these things there? I'm asking what's the probability that I will hit, the next time I do the experiment, I will hit bin J. So I really care what's going on with J. So what have I done to the parameters of all the other bins? I integrate them out. And then what I have is really the marginal posterior of theta j. And what the result is, exactly the same thing with the beta distribution. It comes that the predictive distribution, it's actually the mean of that marginal posterior. It's actually an identical problem with what we did before. You say, let's concentrate on bin j. It has a posterior distribution, phi of theta j given the data. So the predictive distribution is this. And you get nj plus alpha j, n plus alpha 0 from these formulas here. You can see the formula of theta j is alpha j divided by alpha 0. So the posterior had the coefficients, you remember, nj plus alpha j divided by n plus alpha 0. Okay? And you see at the end, this thing avoids the zero count effect. Okay? So basically, if you do an experiment and you never hit bin j, and you ask what's the probability next time that I will hit j, common sense will tell you 0. This will tell you no. Because this can be 0, but this will be equal to 1. Very important. All right, very important. And actually, with this, what I described with this end-one smoothing, right, for I said it is essential if you have problems with limited data. This is even more important in the context of the Dirichlet distribution, because if I have a variable that can take, let's say, 50 different, I can allocate it in 50 different bins, obviously some bins we're not going to have any data. If I only do this experiment 30 times and I have 50 bins, there will be 20 bins with nothing there. So basically, you're going to have less data to be able to do reliable Bayesian analysis. So having this type of smoothing, it is essential. And if you use point estimates like MLE or a map estimate, that is not going to help you. We have actually 2 minutes. So let me do this example to demonstrate this. And maybe you can go in and it's only 2 or 3 slides. Using this concept of bag of words, right? So what we do is we have 2 sentences that you see here. And we basically, the sentences consist of words, totally of a number 10 words that I listed here. And basically, these words, obviously you read them. Ank means, in computer science, means not a known word or an unknown word or something like that. And I emphasize them here with red, okay? So basically, we don't count these words, or we count them as word 10, okay? So
we have two sentences, we have two words, and we would like to actually find what is the probability that of observing, let's say, the word lamp or little, right? Once we have these two, the observations consisting of those two lines. Okay? I'm going to come back to this example because it's interesting, but basically what you need to do is, right? So you can first do a histogram of what words appear in each sentence, and this is the histogram for sentence 1, this is the histogram for sentence 2. So for example, you can see it says there is the word Mary, okay, that's word 1, okay? Head A, that is not a known word, that's 10. And then you have little, which is word 3, etc., etc. And then you start counting how many times the word 1 appeared in the two documents. It appeared twice. How many the word not known appeared? And it's 1, 2, 3, 4, okay? 4 times. So basically from this, you can compute the MLE estimate with the empirical counts, all right? So I will come back on this example tomorrow, but the idea here is there are some words that never actually appear at all in the model. So what's the word 7? The word black. So if I ask you what's the probability on the next sentence that I will see the word black, you should not tell me it is 0, because actually the probability is 1 over 27. Okay? And that is sort of this regularization that comes through the prior model and doing averaging over all possible models. All right, so we will do a little bit tomorrow. We will come back to this example and try to finish to some extent this lecture. All right, so tomorrow we have, I think the lecture is a little bit earlier. It's 11 something, okay? 11:30. All right, so I'll see you tomorrow.